Hello, Fifth. So we're trying practicing a bit of screen recording now and see whether this is a bit less laggy and whether you find this any easier to work with. So hopefully you've watched the YouTube video and seen that water can undergo electrolysis. And what we're going to try and do is just understand that process now. For the main reason is because whenever you do electrolysis of an aqueous solution, then you've got to think about the fact that water is there as well. So you might have, let's say, copper sulfate dissolved, but you'd have copper plus ions that could go and react at the negative cathode, positive, negative. Or you've got sulfate negative ions, two negative ions, that could go and react at the positive anode. But then you've also got water that could react there, and we have to make this decision, and that's going to be the subject of next week, really. But for now, let's focus on what the alternative is, what happens when water undergoes electrolysis. Okay. So first of all, if I can just draw a little water molecule on top, right? No, I can't. Bear with me, I'm going to try and draw a water molecule. Okay. So, on the top right, you should see a little water molecule there. Now, one thing we have to understand about water, which I'll probably put on another diagram as well above this, so hopefully you've seen this already, is that water is polar. Now, it doesn't mean that water has ions, like a positive ion and a negative ion, but it means there is an end of water that's like a tiny bit more negative, and that happens to be the oxygen end, and an end of water that is a tiny bit more positive. Now, because they're not fully positive like a sodium ion, we say delta. And the Greek letter delta means slightly. So we have delta positive and delta negative end of water. Now, that's as weird and wonderful as we need to go with it. You just need to have this appreciation that actually, yes, water is neutral, but the slightly negative end can be attracted to the positive electrode. And the slightly positive end, the hydrogen end, can be attracted to the negative electrode. And then actually a reaction does happen between the slightly negative oxygen end and the positive electrode. And a reaction happens between the slightly positive hydrogen end of the water and the negative electrode. And what we're going to do is look at what happens there. So I'm going to use a bit of highlighting here to kind of, as we sketch along. So let's use a lovely blue colour. Now, these slightly negative end, the oxygeny end of water, is going to get attracted to the positive electrode. And think about what the positive electrode does. Okay, positive electrode is sucking electrons towards it. Okay, so what it actually does, and this is above what you need to know in terms of actually being able to regurgitate this, but this is just going to actually allow you to understand. So please bear with me. What it does is the electrons that are in those bonds, they are sucked towards the positive electrode. Okay, so these electrons, all these electrons there, I'll highlight in green, they get sucked towards the electrode, and what the electrode wants to do really is have some of these electrons. Okay, so as these electrons go there, they leave behind 4H+. These hydrogen atoms now lose their electrons from that covalent bond, so become hydrogen ions. So on the left-hand side, I'm going to draw kind of the after situation, which is you've got 4 of these hydrogen now ions, because those electrons that they used to be in the bonds that tethered them to the oxygen have been removed. And they've gone to the electrode, but not all of them have gone to the electrode, because some are going to be needing to make something that's stable that's got oxygen atoms. And have a little think about what that could be. There we go. And the answer is oxygen molecules. So you actually make oxygen gas. Now, when you think about an oxygen molecule, I'm going to draw it next to the electrode, because that's where it's produced here. When you think about an oxygen molecule, well, oxygen's in which group? It's in group 6. So how many electrons does it need to gain in order to have a full outer shell? Well, 2. Now, sometimes you can make oxide ions, so each one would gain 2 electrons, and that would be a possibility. But actually, wouldn't it be even better if they had to share those electrons so that they could both have a full outer shell and only gain a total of 2 each and make oxygen atoms? Now, the reason you can't make oxygen ions really is that they're not stable. You can't really make them in water at all. They're far too attractive to positive things, but oxygen molecules are neutral and a lot more likely to hang around. So you do make oxygen molecules. Think about the oxygen molecule. They've got 1, 2, 3, 4 electrons there in the oxygen molecule. So we started off with these A text, and you actually, if you're doing a dot and cross diagram for water, then you should think about the lone pairs of electrons on the oxygen atoms as well. So we've got these 1, 2, 3, 4, 5, 6, 7, 8 electrons around oxygen in water, so it's happy, it's got a full outer shell. Now in oxygen molecules, it's the same thing. Still got those 2 lone pairs on each oxygen atom, which means that every oxygen atom feels like it's got a full outer shell, 8 electrons, 4 in the shared region and 2 on the lone pairs. But if you count up all the electrons, you can actually do this. On the 2 water molecules, there's 16 electrons in total that we've drawn. In the 1 oxygen molecule, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons in total on the oxygen molecule. So how many's left over? Well done if you counted 1, 2, 3, 4 electrons are going to be given to that positive electrode and go. Because don't forget, those hydrogen atoms or hydrogen ions do not have any electrons associated with them at all. So now, I don't expect you to remember all that kind of detail there, but hopefully it made sense a little bit in terms of the positive electrode attracted electrons. By doing this reaction, we've given it 4 electrons. That's what it wants. It's sucking electrons away from this molecule. And we've rearranged things so that we make some H+. Every acid releases H+ into water, so they can exist in water happily. And an oxygen molecule, which then floats off as a gas. But again, oxygen is a stable thing that can exist. So it's a process that is allowed to happen because you're making fairly stable things, and you've given the anode, positive anode, what it wants, which is more electrons. So this is a reaction that can happen when water hits the anode. Okay? What I'm going to do now is just put that into words. Okay? So put it into a half equation. So what do we start off with on the left-hand side here? On the right-hand side, as I've drawn it, but I'm going to put it on the left-hand side of the equation because it's a starting point, is 2 water molecules. Bear with me. 2, that's a 2H2O. And well, what have we formed? That's an arrow, apologies. What have we formed? Well, we've formed 4 electrons. They've gone up the anode. You could say that water has lost 4 electrons, so you could put it as a negative 4 electrons on the left-hand side if you like. You've formed an oxygen molecule. And you've released 4H+. And what we always want to do is check that an equation's balanced. How do you check this equation's balanced? Where you look 2 water molecules, so 4 hydrogen atoms on the left-hand side, 4 H+ on the right-hand side, 4 hydrogen atoms on the right-hand side. 2 times 1 oxygen atom on the left-hand side from 2 water molecules, 1 O2 oxygen on the right-hand side from an oxygen molecule. Done. So atoms are happy. Is the charge okay? Everything neutral water molecule times 2 is neutral. You've got 4 negative electrons on the right-hand side. You've got a neutral O2 and 4 positive H+ on the right-hand side as well. So 4 H+, 4 E- cancel each other out. The right-hand side is neutral and the left-hand side is neutral. So therefore, the equation balances. So that's the half equation that goes with water when it electrolyzes at an anode. Okay, and that is worth learning because that can come up every time we do, well, not every time, but it's a possibility every time we consider an aqueous solution. Now, in some cases, it doesn't react, and the positive metal ion, the negative ion that's dissolved in the water reacts instead, actually when there's halide ions, but we're going to talk about that later. But then sometimes when you don't have a halide ion, this reaction does happen, so it happens quite a lot. So it is worth learning that reaction. Okay, I'm just going to stop here because that's 10 minutes. Give a bit of time to digest, and then we'll talk about the other side.